Hi there. Today we're going to carry on our quest to find improvements to the leapfrog scheme. Last time we looked at implicit schemes which aim to improve on the stability properties of forward Euler. Today we're going to look at a scheme often used to try and improve on the accuracy of forward Euler. So forward Euler is first order accurate, remember. Here we've got a scheme that's second order accurate, and we're going to look at the properties, its stability of the leapfrog. Okay, I'll hand over to the board now. Okay, so we've been asking this question, how do we improve on forward Euler? And last time we looked at implicit methods or backward Euler. Today we're going to look at a method that tries to improve on the accuracy. So I'm going to try and look at improving the accuracy from forward Euler. So remember, forward Euler is first order accurate. So there is a method of improving it up to second order accuracy, and this is going to be called the leapfrog method. So with the leapfrog method, start off by approximating our dx by dt in our ordinary differential equation. But this time we use two different time sets. We use m plus 1 and xm minus 1. So it's a centered difference formula divided by 2 delta t. And we encountered this before with our Taylor series approximation, part of the course. And remember, the error then in that case was 1 delta t squared. So in this form, that means it's second order accurate. And this is where the leapfrog comes in, because you're using step m plus 1 and m minus 1. So if we just imagine a timeline where you have m minus 1, n, and n plus 1, we're essentially using these two time points, m plus 1 and n plus 1. So in a sense, it sort of leapfrogs over step n. Okay, so that's where the name comes from. So that's the approximation we explore. So if we then now do the entire ODE, we have the right hand side, which is xn plus 1 minus xn minus 1 over 2 delta t, our first order approximation to dx by dt. And then on the right hand side, we're going to have a function and we evaluate it at step n. That is our leapfrog formula. The question is this method stable? Or maybe a more nuanced question is, when is this method stable? Okay, that's where I was. So we've got second order accuracy. So it's no good having better accuracy without numerical stability. And this is a big reason why this whole area of stability analysis that you may have been introduced to last year, but we're doing in much more detail this year, is so important. You can come up with, I don't know, a 6th order accurate scheme. It might look really flashy on the tin, if you like, as you write it down. But if it hasn't got this property of numerical stability, it's no good to you. So you have to bring in both those things, accuracy and stability. And I make no apology for repeating this idea again and again, that we have to have these two ideas, accuracy and stability, and they have to go hand in hand. And remember, I drew a little sort of seesaw that sort of illustrated that. So we need to analyse the stability of this equation. Let's just write up again the leapfrog. So we now need to consider the amplification factor. And the definition of A is as before, but we need an extra part to this because we're introducing this extra time step n-1. We have to observe that the idea of the amplification factor is this factor that you multiply by each step with the numerical solution. So it takes us from step n to n+1. So the inference is that it should also take us from step n from n-1. Okay, and that's important to write that down at the beginning, because we're going to have algebraic expressions that involve step n+1, n+1, and n. So that's just extending the idea. This shows you understand what the amplification factor means. It's a factor that multiplies each step. So just say A is a factor that multiplies at each step, or every step, each and every step. And that's just really, so you could carry this sequence on. It could be xn-1 over xn-2. We won't need that for this derivation, but that's the key sort of starting point. So now we're going to apply this to our familiar true solutions. The two true solutions we've been considering are the exponential decay and the oscillation. So now this, in this case, then the right hand side is f of x is minus lambda x. Lambda is greater than 0. Yeah, and we then have the leapfrog is then xn+1 minus x of n-1 over 2 delta t. Our left hand side, a second order accurate approximation to dx of t, is minus lambda x of n. So this method is leapfrogging n+1 to n-1 over the xn step. And we can just see that the algebra is just a little bit more involved this time. No, not complicated, but it's just more involved, and we have to be a bit more careful as we set up. So what we're going to do, the first step is we're going to divide by x of n through this whole expression. And that will give us, implies that xn+1 over xn minus xn-1 over xn plus 2 delta t equals 0. So I've also brought the I've divided by x of n and I've multiplied through by delta t, 2 delta t, to get that to that point. Then we can identify that a equals xn+1 over xn, which equals xn-1 over xm. So for this first bit, we know that's A itself, and then the second bit, xn minus 1 of xn, is 1 over A. So we can just substitute for A. That implies A minus 1 over A plus 2 delta t is 0. And what we end up with then is a quadratic equation for if we use our quadratic formula, we get A is minus B on 2A, which is minus lambda delta t, plus or minus square root of B squared minus 4AC on 2A, which gives you lambda squared delta t squared plus 1. So this is the drawback, if you like, drawback or the consequence of now leapfrogging over step n, getting that second order accuracy, is we now have an amplification factor that needs more interpretation. It's not just one value, it's two values because it's quadratic. So what we're going to do is we're going to call the two roots a plus and a minus, corresponding to the plus and minus sign previous. So the plus sign goes to a plus, a minus, and just see what they give us. So a plus is minus lambda delta t plus lambda squared delta t squared plus 1. And now I'm going to use a Taylor expansion. Use a Taylor expansion, the standard expansion for 1 plus x dn, where n is a half. So that gives 1 plus x to the half is approximately 1 plus x on 2 plus the other term. So we're just going to use the expansion of that to get it in a different form, because really I want to see what I'm interested in. We know the true solution is e to the minus lambda delta t, but I'm going to see if this gets into the same form. So it implies a plus equals minus lambda delta t plus the expansion of this term, 1 plus lambda squared. So if just bear in mind the terms that are missing out of this expansion are order x squared. So we're putting x, Rx is lambda squared delta t squared. So we then have lambda squared delta t squared onto plus order, because it's order x squared and it's delta t squared, and there it's order delta t to the 4. Okay, so the remnant term is here. So that implies that your plus root there is 1 minus lambda delta t plus lambda squared delta t squared on 2 plus order delta t 4. So if I said if x is lambda delta t, this has this has the form 1 minus x plus x squared on 2 plus, other terms. So question is, what does this resemble as a Taylor series? So this looks like a Taylor series for something else. What is it? It looks like, so you've got 1. If you're struggling, think of what's 1 plus x squared on 2 plus x squared x cubed on 3. What's that the expansion for? And then change it. So I'll just pause a minute whilst you have a think about that. Okay, so the answer is it's actually e to the minus x. So what we've done, we manipulated this solution of quadratic into a form that looks like an exponential, and because a true solution is an exponential decay, that's going to help us. So a plus, the key thing is that this is order x cubed. So a plus equals 1 minus lambda delta t plus, this bit here can be substituted for e to the minus lambda delta t, okay, x is lambda delta t, plus order delta t cubed plus order delta t4. I'm going to keep that in and show you what to do. Now, of course, when we have these orders, it's the lowest power that dominates, so we don't need to worry about any more about this delta t to the 4. We just have order delta t to the cubed. And we've got exponential decay. So we can see the positive root resembles an exponential decay. E to the minus lambda delta t. So that's helpful. What about a minus? So your negative root, a minus, a subscript minus, has different signs. It's minus lambda delta t minus lambda squared delta t squared plus 1. And we do the same process, expand this square root, and that gives us minus 1 minus lambda delta t minus lambda squared delta t squared on 2 plus order delta t to the 4 again, and then we substitute for this, but this time the signs are different. It actually gives you minus e to the plus lambda delta t plus order delta t squared t cubed, sorry. So the key thing is the a plus resembles the decaying mode, resembles the true solution, it decays, but a minus grows. It's the so-called parasitic or computational mode, and that's what we'll show here, is that actually at the end of all this analysis, for the decaying case, we have something quite nasty here, this growing bit that's going to really dominate the solution and muck it up. So it turns out that the leapfrog is going to be unstable for all cases. So the last stage to do this is to combine our plus and our minus solution into a solution for all n. So it turns out that we can superpose solutions, and so that means x any step n is some constant set by initial conditions, your a plus solution to the power of n. So remember, your amplification factor is multiplying through the solution at any step. So to get the solution at any step, you just take the amplification and do it to the power of n. Plus C2 a minus. And so C1 and C2 are constants set by initial conditions. And then we just substitute our values of a plus and a minus. We then have C1 is a to the 8 plus n. Remember, that was e to the minus lambda n delta t. And the C2 is minus 1 to the n e to the lambda plus n delta t. And I'm going to leave it there because I don't want to rush through this little bit. But you can see there's something really going wrong here. You've got basically what we call the physical mode. Now, if you remember back to that sort of recursion example we did a number of videos ago, we had a bit in there that resembled the true solution, but we also had something that was pathological, parasitic, or computational mode. And alarm bells go out because this has got a minus 1 to the n, so it's already oscillating each step. And then even more alarm bells out that it grows. So it grows. But the true solution doesn't grow. So this is going to always be present there, and we have to deal with that. So I'll use that as a kicking off point for the next video. Okay, see you next time.